So in this slide, we have the FPGA layout and components. So we talked about this a little bit before, but just as a review, on an FPGA chip, there's a couple of different things. So one is going to be your configurable logic blocks. So those are the things that are actually going to be doing the logic functions. So it's going to be doing processing, calculations, and things like that. Another thing that we have on there is the programmable interconnects. And what these do is they route different logic blocks together, and they basically do this to create the functionality that you define in software. Not only do the programmable interconnects route signals from logic blocks together, they can also route them in and out of I/O blocks to get signals into and out of an FPGA. So how does the FPGA work? Again, the programmable interconnect switches and wires route signals between various hardware resources in an FPGA, and this is how it essentially implements the logic that you've defined in software. So hardware resources on the FPGA include things like logic gates, flip-flops, block memory, multipliers, things like that. So if you want a more detailed description of how each of these FPGA components works, you can look at the link shown on this slide. So in this slide, we have an example of a visual example of how FPGA works. So let's say we're creating a VI, and then that VI is trying to calculate a value for f from inputs A, B, C, and D, where f equals A plus B times C times D. So if we look at the FPGA here, we can kind of get a high-level overview of what's going on. So let's say we've got those inputs. So you have A, B, C, and D, and you have those signals coming in through there, through an I/O block. And then those signals are routed to logic blocks on the FPGA, where it's going to actually implement the addition and the multiplication. So then these are all routed, and eventually the result of that signal is routed to another I/O block where it outputs the signal F. So you can see how on the slide the logic of whatever program you're writing is actually implemented into hardware, and there is no OS running here. So let's take a look at some of the benefits of using LabVIEW FPGA. So if you're using LabVIEW FPGA, if you know how to use LabVIEW and also learn a couple of the things specific to programming LabVIEW FPGA that we talk about in this course, you don't have to learn VHDL or Verilog. You can simply use LabVIEW to program the functionality of your FPGA. And if you have something on an FPGA, then you're going to have true parallel execution. And we'll talk about that a little more in the next slide. And then also, because the FPGA is implemented in hardware, it's going to be very reliable and very deterministic. So here we see an example of true parallel execution on an FPGA VI. So notice that we've got two separate things going on, truly in parallel. So if we look at the top one, we've got signals A, B, and C coming through, and we're doing some sort of algorithm on that, and it's going to get output to F. Then we look at the bottom, we've got X, Y, and M coming in, and those are being implemented in a totally separate algorithm, and that's going to output to Z. And if you take a look at that, when it's implemented in hardware, in this case, these two algorithms have no dependencies, so they can run totally parallel to each other. So because it's being done in hardware, this is true parallelism. These two things are really happening on the hardware at the exact same time. If you wanted to, you could add even more things, and as long as they don't have any dependencies, then all those things are happening in parallel. You can have 10 things going on in parallel. Whereas before, if you're working on a computer with an OS, then there's only a certain amount of parallelism you can get. You can only get as many parallel things going on as compared to how many CPUs you have. So one big advantage of FPGAs is you're having these things implemented in hardware, and they are executing truly parallel to each other. So here we see that the FPGA is connected to I/O resources, and it's also connected to a bus that allows the FPGA to talk to the host, or the host to talk to the FPGA as well. So if you take a look at this, if you look at the I/O resources there on the right, for every I/O resource that you have, part of the FPGA resources, so part of that FPGA hardware needs to be used to implement that communication with your I/O. And then similarly, on the bus side, part of your FPGA resources need to be used in order to implement that bus interface where the FPGA can communicate with the host. And then after that, the rest of the FPGA you can use for timing, processing, triggering, calculations, and things like that. So just know that part of that FPGA has to be used for the bus interface and also to communicate with I/O. So let's look at some of the timing benefits of FPGAs. So let's take an example of a multi-loop analog PID loop rate. So on FPGA, these loop rates can exceed 100 kilohertz, whereas if you're running this on a real-time operating system, they can only run, about at 30 kilohertz. So again, on the FPGA, you're going to get faster speeds. Also, with a digital control loop rate, you can execute up to 1 megasample per second or even more, depending on the target. On FPGA, there's also this concept of a single cycle time loop. And with those, you can execute things up to 200 megahertz or more, depending on the target and the clock configuration. And we'll talk about single cycle time loops more in a later lesson. Also, as we saw before, due to parallel processing ability, adding additional computation or adding additional loops, it does not necessarily reduce the speed of the FPGA application because all these different loops and computations can be happening in parallel. Now you can describe aspects of FPGA technology. Next, we will add an FPGA VI to a LabVIEW project and view FPGA function palettes.